Today we will study intermediate code generation. So you might already know that the compiler has some stages. Okay, so now we are starting. Okay, now so you already know that a compiler can be divided into some stages. Okay, so basically you have a source program, and that source program goes through some stages like lexical analysis, syntax analysis, semantic analysis. Roughly these stages we have. After that, these actually, even when this compiler is going through these stages, there also it uses some intermediate code, intermediate representation. When this like this program, you have a source program, and when you give this source program to lexical analyzer, then it will give you some you can say some other like tokenization. Basically what it will do, it will divide, it will convert the given source program into some logical units. Now this will go to parser. So this parser, what it will do, it will make a syntax tree here. So that syntax tree that this parser makes, that itself is a intermediate representation. So these are called high level intermediate representation, because this source program is high level, our you can say high level programming language. So this source program is written in some high level programming language, C language, Java language, whatever. And these first three stages like lexical analysis, parser, and this semantic analysis, these phases are actually close to high level, like these are close to high level, and the remaining phases like optimization and code generation, these are close to low level. Low level means machine level. Okay, because yeah, anyway, so now here the parser creates syntax tree. That syntax tree itself is a intermediate representation. Now after that, this our intermediate code generation, so this stage we have. After the syntax analysis, this is the next stage we have. So we have something called semantic analysis. Okay, so semantic analysis, let's write it as a. So after this semantic analysis, we have this phase, intermediate code generation. This phase actually creates the low level intermediate representation. So when we have this high level intermediate representation, then the intermediate representation that we use, that is syntax tree. So here our parser actually uses the syntax tree representation. Okay, and this ICG, intermediate code generation, so here we use mostly the most popular, if you see the intermediate representation, that is 3 address code. Also let me just tell you before we go further, I am assuming that you already have the knowledge of basic you can say basic compiler design phases like lexical analysis, parser, semantic analysis. So I am assuming that you have the basic knowledge of all these things, the basic working of compiler, like what are the stages and all these things. So that is my assumption. So that's why today we will directly start the 3 address code, which is one type of which is one possible you can say representation for the intermediate representation. And of course we have other possible representations also, but today we will focus on 3 address code, and also we will focus on SSA. So this is the basic understanding I assume that you already have. Okay, so now what I am saying, see, so our focus today will be here, the ICG stage, intermediate code generation stage. So this stage takes the syntax tree. So this will take the syntax tree as an input, and it will convert this so this input it will convert into low level intermediate representation. Okay, now here different compilers can use different representations. Okay, so some compilers use 3 address code. So this is most popular, 3 address code. So most compiler actually use this 3 address code. Some compiler use SSA, static single assignment. So this is another form of intermediate representation. And some other compilers use some different representations. Okay, like syntax tree or postfix notation. So you already know all those things. So today our focus will be TAC and SSA. So this 3 address code and this static single assignment, this actually why we are studying these two things, because my main motive is to teach this compiler optimization. So in this compiler optimization phase, actually most of the time we actually this 3 address code and SSA, these are the two intermediate representation on which this optimization is you can say can be performed very efficiently. Okay, so that's why actually most of the time whenever you will study this compiler optimization phase, at that time you will see that they will be using TAC or SSA. Okay, so that's why our focus today will be on 3 address code and on SSA, mainly on SSA. Okay, so let's see. So yeah, computer science by Sasank, he is asking what is the difference between annotated syntax tree and syntax tree. So Sasank, as I told you that today our focus will be on TAC and 3 address code and SSA. So today we are actually not studying this SDT, this syntax directed definition. Maybe some other day we can take it, and at that time you can ask this annotated syntax tree and syntax tree. Okay, so kindly focus on this topic, because actually the main focus is going to be on the compiler optimization phase, all the newly added topics in the GATE syllabus. This year they have added some topics. Now so let's see what is this 3 address code. And you might be already aware of 3 address code, so that's why I have taken these slides. Okay, so that because you can say there is a lot of theory, so that's why I have prepared these slides. Actually all these slides are just copy paste from Ullman. So from that book I have taken most of these slides. Some slides on SSA are from different books, but all these 3 address slides are from Ullman book. So you can, when you refer to the Ullman book, then you will find all these things. Okay, I have just shamelessly copied those things. Anyway, so what is this 3 address code? First of all, what is this 3 address code? This is an intermediate code representation, nothing more. So this intermediate code generation phase, it will represent the intermediate code in some representation, and this 3 address code is one of the possible representations. And this is very popular representation. That's why actually you can see this has so much hype. Okay, and why it is popular, all these things we will see as we move further. We will see why this is so much popular, because actually this 3 address code, it makes optimization easy. Okay, and our main focus is on optimization. That's why we have taken it. So this 3 address code, what is this 3 address code? The name itself suggesting you that it has something to do with 3 addresses. Basically at most 3 addresses you can have in some instruction. Let's assume you have this instruction. Like many times I have seen many students giving these type of C programs. For example, let's assume this type of C program you have. Okay, so this type of anything, something like that. Now here actually you don't know the order of evaluation. Okay, so you can see what to evaluate first. For example, if I give you A plus B minus C, then what to evaluate first? What the C programming will do, what the C language will do, what the Java language will do, whether they will evaluate this first or whether they will evaluate that. So like these type of confusions actually are there. So in the 3 address code we don't have these type of confusions. Okay, because let's assume you have this statement, and let's assume that your programming language will do the plus first and then a minus. Let's assume then your 3 address code, when your compiler, because of course your compiler is written for your programming language, so in your compiler, when it will convert this high level statement into 3 address code, then it will first calculate A plus B. So it will store it like this, A plus B. Then it will do you can say T1 minus C, and then it will store it in some T2, and then X equal to T2. So let's assume you give this to someone and then you give this to someone. You can see this is clearly very unambiguous, or you can say very precise, this 3 address code. So when you have 3 address code, then things become easy, and when things become easy, then basically optimization is easier. You can do some optimization, you can reduce some statements, you can reduce the size of the code. If your code is 5 lakh lines, then of course you can reduce it. the time complexity, and many more things you can optimize. So that's why you can see. So this is a 3 address code statement, because you can see here we only have one operator. You can see on the right hand side of the assignment. So this is the assignment, and on the right hand side of the assignment we have at most one operator. So this is mostly the 3 address code for the expressions. Like these are the 3 address codes for the expressions. Of course, we in our language we have expressions, we have loops, we have conditional statements, we have many type of things in any programming language. So the 3 address code for the expressions can be written like this. So you have this assignment operator. On the right hand side of the assignment operator you can have at most one operator. Okay, so here you have multiplication, here you have addition. So anyway, so in the 3 address code basically there is at most one operator on the right hand side of the instruction. Okay, so basically no built up arithmetic operation are permitted. For example, this type of expressions are not permitted, x plus y into z, because we don't know what to evaluate first. Okay, so that's why this 3 address code is, you can say, is a better way, you can say. Okay, because we do not allow this type of expressions. Okay, so so this is the definition of 3 address codes. And of course, when your compiler is converting your high level language code into 3 address code, then to convert your high level statement, for example this statement is high level statement. Now when your compiler is converting this statement into 3 address code, then it will convert like this. So it has to make some temporary variables. So these T1 T2 are compiler generated temporary names. Okay, and basically what you have done, you have just unraveled this statement. In this statement you have 2 operators, so you have basically just you unfolded it. Okay, and anyway we will see more 3 address code, like for loops what kind of 3 address code you have, for conditional statements, for function calls. So all those things, let's see. So first of all, before we see the 3 address codes, let's see the conventions that we will use. Okay, so what is an address? Okay, whenever, for example, when you write this type of statement, x equal to y plus z, then of course this is a variable name, this is a variable name, this is a variable name, but still we treat them as an address. Okay, so this is the convention actually, because actually see what happens is when your lexical analyzer is doing something, and when your syntax analyzer, semantic analyzer, when they are doing their things, at that time what they do, they store variable names and their attributes in the symbol table. So this is your symbol table. Now so what they do, they store the variable names. For example, if you have a variable name x, then it will be stored like this, x, and then its data type and its attributes also. By attribute I mean, like in semantic analysis phase you have attributes. Okay, when you study SDD, SDT, at that time you can see every non-terminal or every variable basically has some attributes. So you have those attributes also here. So you can see actually in the symbol table, of course the symbol table access should be faster. So this symbol table can be implemented by hashing or something. So when we use in our convention, this is the convention that we will use, that in our 3 address code, when we will use this x plus y, so this type of statement when we will use, it will mean that this x basically means that this location in the symbol table, the location where we have stored the you can say this is the record, I can say this is the record for x. So actually this is nothing but a pointer to that location. Similarly this y means this is a pointer to that location. So in the symbol table you have a record for y. For this variable y you have a record, you have many things. Okay, its type, its attributes, so many things you have. Okay, the things that you have recorded. So basically in the symbol table you have a record for y, and here this y actually is nothing but a pointer to this record. Okay, in the symbol table. So this is but for the convenience, what we do, for the convenience we use these names. Okay, instead of the pointers we use these names. Okay, so this is the convention basically we use for convenience. We use this, we do this kind of things. Okay, So but of course in the implementation, of course, when you practically implement this 3 address code, or you can say intermediate code generation, when you do those things, when you implement them, then of course these names are actually not there. These are replaced by the pointers to the symbol table entry, because in the symbol table you have entry for each variable. Okay, who creates that entry and all those things are you can say in lexical analyzer is the scanner. Okay, so whenever it sees a new identifier, then it makes it creates an entry. Okay, then of course the other phases like semantic analysis, okay, syntax, so they can also insert, add information or retrieve information from the symbol table. Actually the symbol table is you can say visible, or you can say this symbol table is used by all the phases. Okay, from the first to the last, all the phases actually use the symbol table. They can insert some information, they can retrieve some information. Okay, so so this is the convention this we use. So basically from now onwards, every name of the variable itself is an address for us. Okay, so whenever we write this type of statement, these names are also address for us. Okay, so this is one address, this is another address, this is another address. Okay, a constant also we treat as a address. Okay, so anyway, next so basically when you write this type of statement like x plus 20, then here this 20, this constant is also treated as a you can say address. Okay, now then we have compiler generated temporary variables like t1, t2, those, so those are also addresses. So we have these three type of addresses in our 3 address code. Now so what is this? Also let me tell you one thing. Whenever you will see actually this compiler design subject when you study, because of course this is a practical subject, this is not a theoretical subject. Like TOC is a theoretical subject. Okay, discrete mathematics is a theoretical subject. Whatever you study, that like that will not change. Okay, but of course the concepts that you study in compiler design, they are not universal concepts, you can say. For example, the concepts is saying something and the implementation is doing something else. Of course there are many compilers, and they have their own at 3 address. For example, you have some compiler. Okay, like Stanford University has some compiler, I think I've forgotten its name, but it has like when you study the compiler design course from the Stanford University, then basically they are taking a compiler and they are teaching you that compiler. They are teaching you all the concepts which revolve around that compiler. Okay, so that compiler has its own 3 address code instructions. The basic idea is same. Like you must have at most 3 addresses, so that basic idea is same, but of course the particular instructions may be different. Okay, so for our discussion of 3 address code, we will use the 3 address instructions that this Ullman book is suggesting. But just let me tell you that whenever you have some particular compiler, whenever you have some actual compiler, actual practical compiler, then that might have its own 3 address instructions. Okay, I will tell you some you can say some differences I will tell you. So we will use basically I'm just following this Ullman book as it is, I think, the most standard book for compiler design. So this assignment type of instructions are 3 address code. Okay, so for example, when you have this type of instruction, then this is 3 address code instruction. So we can use this type of instruction in our 3 address code. Okay, and of course this is just assignment instruction, and we can also have like x equal to x plus z. This type of instruction also we can have. Of course we should have at most one operator on the right hand side of the assignment. So this is the assignment, and we should have at most one operator on the right hand side of the assignment. So this type of instructions are 3 address code. Okay, here x, y, z are the addresses, of course. Okay, next so for example, when you have this type of instruction, x is basically assigned the value minus y, so this minus is the unary operator. Okay, so this type of instruction is also allowed. So this type of instruction is also 3 address code, and of course this minus could be any unary operator. Okay, logical negation, okay, or any of these unary operators like shift operation, okay, conversion operation, any these type of operation it could be. So this type of instruction is also 3 address instruction. Next, The third, this assignment instruction, like copy instruction, you can say x equal to y. So basically x is assigned the value of y. So this is also 3 address code instruction that we will use. And the fourth is our unconditional jump. So basically go to L. This L is label. So when you write the 3 address code, then this L is basically label for some instruction. Okay, of course it depends on the implementation whether you use this label or whether you use some pointer. So that depends on the implementation. Here we will use the label. Basically this instruction has this label. Okay, so go to L means just unconditionally, just directly go to the instruction which has the label L. Okay, so next we have conditional jump. So for this conditional jump we have this type of statement, like you can, if x, basically if x is true, it means if x is true, then go to L, so this type of this is also 3 address code instruction. And also we can use this, like if I want to say that if false x means basically if x is false, then go to L. So this is also allowed. Also I can use this type of instruction, like x some operation, this is some relational operation, and then go to L. So this is also allowed. These three are also 3 address code instructions, okay, that we will use. Of course, as I told you, see earlier I told you that when you have some specific compiler, then you can have, that compiler can have its own 3 address code instructions. So for example, these instructions, okay, we are using because of course the Ullman book has given these things. But when I was studying the Stanford University course, they were using some different 3 address code for these conditional statements. Okay, so anyway, that's why for example they were not using this. They did not allow this. If x op y go to L, they did not allow this. So instead what they did, for example, whenever they were doing this, for example, if you have this, if x less than equal to y go to z, so this is allowed. We are allowing it. Okay, but in that course of Stanford, they did not allow this type of statement. So what they were doing basically, so first they were calculating it separately. For example, maybe t1 is like this, so maybe t1 assigned x less than equal to y. Okay, so then they were doing like this, if t1 go to z. So you can see things actually you can say things can change when you do the practical implementation, because of course all the different compilers, they can use some different things. Okay, similarly in DBMS also you can study the SQL that we study, the basic you can say the theoretical concepts, the basic theoretical concepts of SQL that you study. For example, those concepts actually say that you have this select, and if you have a group by clause, then the attributes that you have used in the group by clause, they also should appear in the select clause. So these type of rules this SQL has. But of course, when this SQL is implemented by Oracle or some other Microsoft or some other, they can for their convenience they can do their own practical implementation. Okay, so like I think in Oracle, or I think in some other implementation, this restriction is not there. Okay, you can use this restriction, like the attributes that you use in the group by clause, you have to use in the select clause. That restriction is not there. So you can see these type of things happen when you study a practical subject. So this compiler design is not a theoretical subject. So, and also why I am telling you all these kind of things, because I have seen students fighting over these kind of things. Okay, like if some student has seen this, let's assume he has studied this 3 address code from one book, then let's assume that in that book they do not allow this. Let's assume in that book they do not allow this, they only allow this. Then that student will be fighting with another student who allows this. So that's why I am telling you all these kind of things. Anyway, so what I'm saying, yes, conditional jump, like if x go to L, this type of statement is 3 address code. If false x go to L, this also we allow. Okay, so what is the behavior of these statements that you already know? Basically, if x is true, then you will directly go to the instruction that has the label L. Similarly, if x is false, then you will directly go to the statement which has the label L. Okay, so now yeah, this type of instructions also are 3 address code. Okay, so like as I told you, if x less than equal to y, go to z. So these type of instructions, go to l some label, go to l some label. So this type of instruction is also 3 address code. Yeah, and what is the 3 address code for the function calls? So if you have this type of function like p, x1, x2, xn, so basically this function call has n parameters, you can see n arguments. So for this function call, when you write the 3 address code, then you can write like first you define all the arguments, like you can say this is the parameter, this is the parameter, this is the parameter. So you have n parameter, so you define them, and then you can write call pn, means this is the function, and these many arguments it is taking. So this is how you can write the 3 address code for the function call. This is the function call. For the function call you can write like this. Okay, next, yeah, so this is important actually. This is important, and also this is I have seen many students doing wrong, like interpreting it wrong. So in the 3 address code, when you have this type of instruction, like let's assume you have a 3 address code. So in the 3 address, so this is 3 address code. In the 3 address code, when you have this type of instruction, then this is not an array. Some students actually say that this x is assigned the value of y and this I. So basically they think of this as an array. And of course many coaching faculties also teach like this, that okay, this is like array. No, this is not array. This is your, in CO you study something called indexed addressing mode. This is that. Okay, so when you have a 3 address code, at that time, remember this 3 address code is actually close to assembly language. So this is very close to assembly language code. Okay, so and this assembly language code you study in compiler optimization. This in compiler optimization we have this assembly language. So there when you when you see this type of statement, then you do not think of it as an array, you think of it as a indexed addressing mode. So this is the like in 3 address code, when you have this type of instruction, then this means indexed addressing mode. This is not array, remember. Okay, of course when you have a high level language, in that language when you have this type of statement, then it means array. What is the difference? I will tell you. Okay, like you might be wondering like what is the difference between array and this index addressing. This I will let you know very shortly. Okay, but anyway, so just you can see, just remember this point till we see some example. Just remember this point, that this type of indexed copy instruction of the form, like x goes to x is being assigned the value of, this is not an array, remember. This means basically this y is some address, and this I, because you know what is this indexed addressing mode, you already know this thing, indexed addressing mode. In indexed addressing mode, what we do, so we have some address, this is the base address, and this is the basically displacement, you can see. So this, what is the meaning of this x equal to yi? The meaning is that you set so basically you assign to the x the value for example, this is your y. Let's assume this is your y. Basically this y is this address, let's assume, and this I is, let's assume, 4. Then basically what you do the displacement of 4 unit. So basically this is your yi. So this is the meaning. Okay, now okay, let me tell you the difference between this and the difference between array. So in the high level language, let's assume you have array. This is your array and this is your A, and these are the elements. Let's assume some element A, B, C, D is there. So this has the index. Of course index is starting from 0, let's assume. Then this is your array. In this array, when you write this A1, then it will give you B. Okay, now let's assume that, so this is high level language. Okay, now in 3 address code, what will happen? So let's assume that each cell, basically, okay, each array element has, let's assume, 4 bytes. Okay, 4 bytes. So in 3 address code, what you will write? Okay, so this, let's assume this is your address 100. Okay, and every every array element basically has 4 bytes. Then when you write A1, then what it will mean? It will mean basically 100 plus 1. This it will mean. It is not, of course, this when you want to access this B, then the address of B is going to be 104. This is the address of the B. But remember, when you write in the 3 address code, this A1 is going to mean this location, this address. Okay, this A1 is not going to mean the address 104. So because you can see, as I told you, this 3 address code is close to the assembly language. Okay, it is not close to the high level language. Okay, so that is the one difference that I have seen many students are making this type of mistake, and sometimes they are getting confused in these type of things, because some at some places, okay, this means array, some places you have to multiply with 4 or 8. So basically, if your element has size, let's assume each element has size 8, then sometimes you have to multiply with 8. So sometimes you are doing this A plus multiplied by A, sometimes you are just doing this. So like when you are doing this type of like difference, students, I have seen some students, they do not know this difference. Okay, they are just either they have by hearted, or I don't know, whatever, but this is the difference. Basically, whenever you have a program which is in assembly language, or which is in like 3 address code, or which is in the low level language, means machine language, then basically these things are not array at that time. Okay, when you go to the assembly language, at that time there is no such thing as array. At that time you have addressing modes, you have indexed addressing mode, you have other addressing modes. Okay, so this is the idea basically. Okay, so anyway, so basically you can see x, when you assign to x, when you assign this yi, then what it means? It means the location I memory units beyond location y. So this will be assigned. Okay, now the instruction xi equal to y sets the contents of the. So basically, what is the meaning of this? The meaning of this is that this value of y will be assigned to x plus I directly. Okay, x plus I. So this is how these things work in the 3 address code. When you have this instruction in the 3 address code, then it will mean x plus I. When you have this same instruction in high level language code, then it is going to mean, you can say, x plus, for example, let's assume each element has 8 you can say 8 bytes, then it will mean x plus 8i. So this is the difference. Okay, we will take one example also. At that point of time it will be more clear. And this is basically just address assignment. Okay, you can assign like x, go to the x, you can assign the address of y. Similarly, so basically x equal to star y and star x equal to y. So these are also 3 address code that we can use. So these are the 9 3 address code that this Ullman book has defined. They are basically converting their all the programs into the 3 address codes which use these 9 instructions. Okay, they are basically using only these 9 instructions. Of course, you can have some particular compiler which will have its own 3 address code, and that can have its own instruction. Maybe that can have some more flexibility. Maybe that can give you 20 or 30 instructions. Okay, 3 address code instructions. So maybe you can have some other some more flexibility. Okay, but anyway, these are the standard, you can say, 3 address codes that this Ullman book has given. So of course, for our gate level, we are going to consider these things. Now let's assume you have this. Okay, before we move on, anyone has any doubt, then you can ask. Anyone has any doubt right now? Yes? You need to remember all these 3 address codes. I would suggest that from gate point of view, like these are the standard books, and see, when Ullman is teaching compiler design, at that time he is not taking any particular compiler. So he is just teaching the basic concept of compiler design. So I think that these nine 3 address codes, okay, you should know. Okay, and I think in the gate exam, of course in the gate exam they are not going to follow some particular compiler. All these things I told you, so that you do not fight with other students and you waste your time. Many students waste time on very silly things. Okay, so that's why actually I have told you all these things. But these three address code, they which are defined in the you can say Ullman book. I would suggest that you know these three address codes, and whichever program you have, then you can, using these codes, using these 9 instructions, you can convert that program into three address codes. Okay, so is this clear, Subhajit? So actually most of the time only these expressions, okay, most of the time they are in the gate exam. So far they have only concentrated on the expressions only. They have not focused on you can say loops, conditional, these kind of things they have not touched yet. So far I think like if you see all the gate questions, then you will see that only these expressions are there. Like you have some expression, and when you convert the expression into three address code, then it just becomes very easy. Okay, like when you convert some expression into three address code, then this type of statement you are going to use. Basically this type of statement you are going to use. Okay, so you can see these you in all your gate questions, you can see this type of three address code will be, you will see. Okay, or maybe I think 1 or 2 questions are there in the gate exam which have touched this array also, like okay, or you can say this index addressing mode, like ai goes to x. So these two things have been touched so far, but other things like function calls and those things are still, you can say still they have not been asked. Okay, so anyway, these 9 are very basic three address codes. Okay, it is not very hard to remember these things. You can understand if you like. Today you can do one thing. You can go and you can read these 9 instructions. You can see in the Ullman book they have just given like every single thing they have given in a very detailed manner. They have given what is the meaning of this address code. This is also given. What is the meaning of this address code? This is also given. Okay, so you can see you can just go through these 9 rules, 9 instructions, and I think these you should know. So let's see this do I equal to I plus 1 while this. So using these 9 instructions that we have seen, okay, using these 9 three address code instructions that we have seen, let's convert this high level language statement into three address code. So of course, again, as I told you, see, as I told you, either you can use the label, okay, or you can use some okay, you will see here. Yes, so this is one possible address code and this is another possible three address code. Okay, in this three address code, what you have done, basically you have given label to the instruction. So this instruction has been given this label. Okay, so you can see here basically we are using the labeling. Here what you are doing, we are giving some address, like okay, this instruction has address 100, this instruction has address 101. So now you can use this go to 100. Anyway, these are the two ways basically. You like, it depends on your in gate exam, it depends which they have used. Most of the time actually, sometimes they will use this, sometimes they will use this. Okay, as I told you, this three address code, this is just a concept and it can be implemented in different ways, but the basic concept will remain the same. Now in this you can see, of course, what is being done here. You will first calculate I plus 1. Of course, what is this statement? See this statement. In this statement, let's assume yeah, this is the C language statement. In this statement, you already know that the C language, what it will do, it will first calculate this and then this condition will be evaluated. So first this do statement will definitely run. So this I plus 1 can be given to T1, then you can assign this. So this is the first three address code you can do. Then I equal to T1. Then what you can do, so yeah, this has been done. Now you will do this A of I. See, this A of I is in the high level language. Okay, now this is like this. Let's assume that each element has 8 bytes. Then what it will mean, it will mean like this. Let's assume this is the base address. Okay, and this I if this is the I index, because remember here this I is index, because this is the high level language instruction, so this I here refers to the index. So the 100I, basically when you convert this 100I into the address, then it will become basically 100 plus, let's assume each element has 8 bytes, so it will become 8 into I, so it will become like this. Okay, and of course the 3 address code is close to the assembly language code, so that is what you will do. First you need to calculate 8 into I. Okay, so you need to calculate this 8 into I first. Okay, because why we are calculating this, because when we use this instruction AT2, when we use this instruction, at that time this instruction is going to mean that this is the base address and this is the displacement. Index addressing mode, in the index addressing mode we do this kind of thing, we have a base address and we have some displacement, so this T2 will work as a displacement. For example, let's assume I equal to 1, then basically this T2 will be 8 and this will mean A plus 8. This 8 is the displacement, you can see from this A. So that's why we calculate this I into 8 and then we assign it into T2 and then we calculate T3 equal to 82. Okay, so I'm repeating again, this is not the array, like this is not an index, this is not an index. Okay, so and so then what we do, then basically we can do this conditional jump. Of course this is the conditional jump, that this value, if this value is less than this value, then you can again jump to the label I. So yeah, so if this value T3 is less than V, then you can go to L, and this L is this. Okay, so this is one representation, this is one possible 3 address code, and this is another possible 3 address code. Okay, so like this is one possible set of statements in 3 address code, this is another possible set of statements in 3 address code. Okay, so like this and this. Anyway, so both are very similar. My main intention was this, because in the GATE exam this type of questions have been asked. I think 2 or 3 questions are there, you can just check it out there, these are there. Okay, now so yeah, this paragraph is also given in the Ullman book actually. So like in the, when you are defining the 3 address code, okay, at that time what operators you are taking, what type of instructions you are allowing, all these kind of things can vary. But basically the Ullman is saying that whatever compiler you make, whatever type of instructions you allow, whatever operator you allow, it must be rich enough to basically cover all the programming concepts, basically all the programming statements, all the programs, all the language programs must be, you know, converted into the 3 address code. So that is the only minimum requirement, you can say this is the minimum requirement. Okay, of course, like we have seen 9 statements, 9 3 address code statements we have seen, but when you write your own compiler, at that time maybe you can give some flexibility, and maybe you can give some 50 3 address code instructions you can give. So this is what Ullman is saying, basically your operator set and of course your instruction set, all these kind of things must be rich enough so that you can implement any operation of the source language. Now after this 3 address, so actually this in the 3 address code, what is the thing that is remaining in the 3 address code? What is the implementation, like how we implement it? Okay, so this is remaining, and I leave this up to you, you can study it, you can read it. So when we implement, so these are the concepts of 3 address code we have seen, but when you implement it, then like how do you implement it? Okay, how do you store it? So for the implementation we have 3 techniques. The one is quadruples, another is triples, and another is indirect triples. Okay, you can just go through, you can read the Ullman book and you can go through this. So this, in the quadruple, basically what we do, this quadruple is what it is. It is a like how to implement the 3 address code. You have a 3 address code, let's assume this is the statement you have, let's assume like this T1 plus T2, and then let's assume T3 is assigned the value of X something. Okay, I'm just randomly writing anything. So for example, maybe T4 is equal to minus X. So like something like this. Let's assume this is your 3 address code. Now how to represent, how to store this 3 address code, how to represent this no, this is representation, but how to store it in your system. So for that, this one technique is quadruple, another technique is triple, another technique is indirect triple. So in this quadruple, basically what you do, each 3 address code is treated as a record. So basically for each 3 address instruction, for this, you make a record, like just like a database. In database you have records. Okay, this is a record, this is a record, and you have some attributes. So just like the database is stored, similarly this quadruple also works. Of course, all these things actually work like this. Okay, in all these things you have records and you have some fields. So in this quadruple, basically we have four fields. The one field is result, so this is our result. This is another field, argument 1. This is field argument 2, and this is the field operator. So we have basically 4 fields in the quadruple. Okay, for example, if you have this statement, x equal to t1 plus t2, then the result is basically x, the operator is plus, and the argument is t1. The first argument is t1, the second argument is t2. So this is the record that you will have in your quadruple. This is the record that you will have. So here, when you have this type of statement, at that time we do not put this assignment. Okay, we only put this operator plus in the operator field. We do not put this assignment here. Just remember this thing. Okay, like maybe some convention, or like whoever gave this idea of quadruple, maybe he gave this, that okay, whenever you have this type of statement, x equal to t1 plus t2, this type of statement, at that point of time in the operator field we do not put this assignment. Okay, so now for example, if you make the field record for this t3 equal to x, then at that point of time the result is t3. Okay, the first argument is x, there is no second argument, and the operator is equal. So remember, here actually we do this. So when we have basically this copy instruction, this t3 equal to x, what is this? This is just copy instruction. So when you make a record for copy instruction, at that point of time you can see the result is t3, the first argument is x, thus there is no second argument, and this assignment operator, this equal operator, is put in the operator field. Okay, so this is the difference. Like when you store this instruction, at that point of time you put here this assignment, but when you store this instruction, at that point of time you do not put this assignment. Anyway, this t4 equal to minus x, this also you can very easily, this is the result, this is the t4, and the argument 1 is x, the operator is minus. So here again we do not put this assignment, and there is no argument 2. So anyway, this is how you can do. You can just go through the you can see this quadruple in the Ullman book. And one more thing I will suggest. Okay, this is just my suggestion. Whenever you have some doubt in some topic, then at that point of time, I have already mentioned many times that you just do a Google search, simple Google search you do, and go to the university articles. Okay, many students actually send me doubts from, like they send me statements from Geek for Geeks, from like Get Vidyalaya, Tutorial Point. Many websites are there. Of course, when you do any Google search, then the top results are going to be these. Please don't use them. Even the Geek for Geeks, this is for the BTech students. This is very unreliable website. Many things are wrong in this Geek for the. All these things are very unreliable actually. When you can have reliable thing, then why to go for unreliable thing? That is the point. Okay, so just go to the, maybe in the first page, if you do not find, then just go to the second page. There you will definitely find university articles. Study from them. Okay, so this all these topics also you can just Google search and you can study from some university article. Okay, so now what is this triple? This triple is actually similar to quadruple, but actually you can see in this quadruple there is one redundant thing, and that redundant thing is this result. Okay, let me tell you why this is redundant. So when you have this type of statement, x equal to t1 plus t2, you already know that this is a 3 address code. You already know, and you are representing this 3 address code instruction. Then if I represent only these 3 information, like if I give you this information t1, that this is the argument 1, and if I give you the information that the argument 2 is t2, and if I give you the information that the operation is plus, if I give you only this information, then also it is sufficient. Okay, what you can do, just t1 plus t2. Okay, so the result, okay, if I ask you what is the result, so like there was a result field in the quadruple. If I remove that, then how can you get result? Very easily. For example, okay, what you do, you remove that field, okay, and this is your, you can consider this is your first, you can say, of course, if let's assume this is a hash table, then this is your first instruction. So this like this one means this is the first record. This will represent the result. For example, now if I use this x, let's assume I use this x, t2 equal to x plus t3, let's assume I do this, then what I can do, very easily I can do, so the result I do not need to store. So the first argument is x, the second argument, the first argument is x, but there is no x, you can see there is no x here. So what is the first argument? The first argument is 1. Basically this 1 will mean that just go to the first record. So this is the first record, just go here and just calculate it. So basically when I write 1 here, then it will mean that you can go here and you can calculate it. So t1 plus t2. So basically this 1 is nothing but t1 plus t2, and this second argument is t3, and the result the operator is plus. So this is how. Now if you use t2, if at any point of time if you use t2, then what you can do, you can use this location 2. So this is how you can basically save some space, you can save. Okay, so this is how you can do. So in the triple, actually we can save space. In the quadruple there was an unnecessary thing. Now we can save space, but of course when we save this space, then some drawbacks also come, and the drawback is that let's take one example of quadruple, and let's take one example of triple. Let's assume you have, in the quadruple you have this type of statement. This is the result t2, and this is the t1, t3 and plus. So this is the result, this is the argument 1, argument 2, and this is the operator. In the triple, how will you store them? You will store them like this. Argument 1 is t1, argument 2 is t3, and the operation is plus. Now you won't store the result, so the result actually will be automatically we will know this result by this location. Okay, by this location, by the location of this record, we will know the result. But now what happens is, let's assume this one you have used somewhere. Okay, so this one you have used somewhere. So this type of record you have. Okay, now actually you cannot do any movement. Let's assume that you have some record here, some record here. This record is there, and this is completely unrelated record to this record. So you have this record, let's call it 3, 4, 5. Now in this record 4 you have used this 1. Okay, this record 3, record 5, they are completely unrelated. Let's assume completely unrelated to record 4, but still you cannot move these two records. Now you will be asking what is the need for this movement, like what is the need for this to move this record 4. Actually it will come in the compiler optimization. So when we do the optimization, at that point of time we need to do this kind of movement. Okay, let me give you the example. When you study pipelining, in this pipelining, when you want to reduce the WAR, WAW, these type of hazards, when you want to reduce, then also the compiler does the movement, if you remember. So in the compiler, in the pipelining, you study this concept that we can basically what we can do, we can shift the instructions. Like if this instruction has no dependence, then we can shift these instructions. Okay, we can exchange these instructions. If this instruction 3 we can move, you can say we can move it ahead. So these type of things you see in pipelining, and there you study one line that compiler does these things. Compiler inserts the NOP instruction, compiler does this type of movement. These type of things you study in pipelining. Okay, of course there you do not focus on these things too much, but the thing is sometimes we do need to move the instructions. Okay, like of course maybe for efficiency, maybe to get more efficiency. Okay, so to reduce the hazards. So this is one example of why we sometimes need to move the records. So the thing is, in the triple, in this representation, in this triple implementation, we cannot move the records very easily. For example, if I move this record 4 with record 3, then what it will mean, now this record now if I remove this record 1, now if I move this record 1, let's assume I move this record 1 somewhere in the second place, I moved, so this record has been moved to second place. Now when I move this record to second place, then what I will have to do, at every place where 1 is there, I will have to change it to 2 at every place. So this is the drawback for triple. So because the movement is not easy, the movement is not efficient. In quadruple we don't have this type of restriction. Of course, whenever we can move, we can definitely move without any, like let's assume this instruction, this is record I1, this is record I2, and let's assume that they do not have any dependence between them. Then what we can do, we can definitely move them, we can extend them, we can put I1 here, I2 here. Okay, no problem, compiler can do this without any worry, without any changement, okay, anything. But in triple, the compiler cannot do these things efficiently. Okay, we will have to do these kind of things. So this is the drawback of triple. When we have this type of drawback of triple, of course the triple has some advantage and has some drawback. Then we have another representation which will reduce the drawback of triple, and of course basically it is like you can say the benefit of this indirect triple. So we have this another implementation, indirect triple. So the benefits of this indirect triple are what? It reduces the drawbacks of triple representation, and basically it gives us some you can say more benefits. So it is similar to triple, exactly same to triple, but in this what we do, okay, in this actually we have some separate, we have a separate you can say list of locations. For example, like this I should have taken example from the Ullman book. So actually, okay, let's do one thing right now. I can't remember some example, but the thing is, you can read this indirect triple from the book. What we do, we separately store all the pointers. Okay, so all these pointers we separately store. For example, let's assume this pointer is pointing to record number 6. This is your triple representation. This is argument 1, argument 2 operator, and let's assume this is record 6. Then we store this 6 here. Okay, now whenever we have to move something, let's assume that you have this record is 6 there, and let's assume this record is using 6. Okay, now if you want to record, this is record 8, let's assume. Now if you want to move this record 6, then what you will have to do, then all you have to do is just like this. Actually we do not store 6 here. What we do, we store this location. For example, let's assume this location is specifically given to the record 6, let's assume. So this location we store it here. So what we do, let's assume this location is R1, so we store it here. Now whenever you move this 6, and this R1 has 6, let's assume. Okay, now whenever we move this 6, then what we do, the only thing we need to change is this one element we need to change. Okay, so this is the basic idea. Of course you can study it from the Ullman book. You just study, they have given one example there. You can see how this indirect triple works. Okay, and this is actually similar to register renaming. Okay, in the pipelining we have something called register renaming. So this concept of indirect triple is very similar to register renaming. Okay, so this concept that we have, register renaming. Of course, to tell you why these two things have some relation, I will have to teach you this register renaming. This register renaming actually uses two concepts from compiler design. One SSA concept is used, and another concept that it uses is indirect triple concept. These two concepts are used by this register renaming concept. You must have studied this. Like there is a gate questions, like when you do register renaming, at that point of time all the hazards are, all the WAW and all the WAR hazards, they just disappear, all of them. Okay, all of them, they're like, once you do the register renaming, then no WAW and no WAR hazard will be there, all will be gone. We will see this. Once we see this SSA, then we will see the proof of this automatically. Once you see the SSA, automatically you will see that all the WAW and WAR hazards are gone. So actually this register renaming, you can see, once you study this SSA plus indirect triple, you just mix them and you will get your register renaming. Okay, so when you study this concept, you will see that this concept is very similar to the mixture of these two concepts. Anyway, a little bit of it we will see. So now we will start the next topic, that is SSA, static single assignment. Anyone has any doubt before we start that topic? Anyone? Okay. Yes. Right. It will calculate, like when you, yeah, that is the disadvantage. So that is one drawback. So when you refer to the one, then basically it will calculate just t1 plus t2, so like that. Okay, so this is like you can see, of course, this is the drawback, but it saves a lot of time. Okay, when you have a program, nowadays you can see there are so big programs, okay, like terabyte programs are there. So at that point of time, space also becomes a very big issue. Okay, so that's why this type of you can say these type of tradings, like, okay, it is kind of like some trading like between the efficiency between the time and space. Okay, so that's why this triple we have. Then after this triple we have indirect triple. So this indirect triple actually reduces the drawbacks of the triple representation. Okay, so of course this has some drawbacks, and this is one drawback. One possible drawback, as I told you, movement of records you cannot do efficiently. The second drawback is this calculation, like every time actually we have to calculate it. Okay, so these are the two drawbacks that we have in the triple representation. And this movement drawback can be you can say we can reduce this movement drawback using the indirect triple. Now let's see the next topic, that is SSA, static single assignment. So this is a very actually interesting topic, and in the GATE exam also they are asking questions from this topic in the recent years. You can see in the last few years they are asking questions from this topic a lot. I think every year they were asking. In 2020 they did not ask, but anyway. So what is this static single assignment? So in this the name, okay, let's see. Static, what is the meaning of static? The meaning of static is that it works on the program, on the text. Remember, it works on the text. Basically you have a program, okay, you give me a program on a copy pen, okay, you give me a program on paper. Basically do not run it, okay, do not run this program, just give me the text. Just give me the text of the program. Okay, now on this text of the program I will do this, basically this SSA will work. So this is the name static. Static means basically this, we will see some examples and it will be clear what do I mean by running the program and what do I mean by static. So basically this static single assignment is a, first of all, this is a intermediate representation. First of all, like just like we have 3 address code, similar another representation that we can have is SSA. This SSA is very similar to 3 address code. Actually it is so similar that some students actually think that they are same. They just think that this SSA is a special type of 3 address code. So because they are very similar, you can see this SSA is very similar to 3 address code, but actually they are different. So this is one possible representation, this is one possible intermediate representation, this is another possible intermediate representation, this SSA. Okay, these are completely different concepts, but these are similar in nature. We will see some similarity. Now the name, first of all, this is an intermediate representation, and what is the meaning of this name? Let's see. Static means it will basically, you give me a text, and on that text I will convert this text into SSA. Okay, so okay, with examples it will be clear. What is the meaning of single? The meaning of single is that we do not assign any, if you have any variable, let's assume you have this variable. Now we do not assign this variable more than one time. So let's assume to this variable x I assign t. This assignment will be called defining. Okay, from now onwards, whenever we will study compiler optimization on, or when we study this like this SSA or compiler optimization, at that time this assigning will be also called defining. So when I say that x equal, this is definition, actually this is the definition for x, or you can say this is the assignment for x. Okay, similarly if I write the next line x equal to t2, this is another definition. Okay, or you can say this is another assignment. Now okay, don't confuse this definition with your high level language definition. Don't say that like in the C language we define one time and these kind of things. Okay, so this is terminology that we use in SSA or in compiler optimization. This is how we use all these terminology. So from now onwards, this assigning means defining. Okay, so what this single assignment basically single definition. This is the meaning. Single assignment means single definition. So if you have this variable x, then this variable cannot be defined more than one time, or this variable x cannot be assigned more than one time. So like here you are assigning x the value t. Now you cannot assign the value as x t2. If you want to assign, you have to take some different variable. So x2, some different variable you have to take. So this is the name SSA. Of course we will take more examples and it will be clear. Let's see. Now first of all, why we study this SSA? Okay, why we study this? Because why I am teaching this SSA before we start this compiler optimization? Because you will see that many compiler optimization, they work more efficiently on SSA. If I give you a 3 address code, also if I give you a SSA, now these two things I give you. Okay, for the same program I give you TAC and I give you SSA. Now if I ask you to do the optimization on these on this program, on these two representations, then you will see that this SSA gives a lot of advantage. Like optimization just becomes very easy. Many type of optimizations, okay, become very easy on SSA. So that is why we study SSA. And many compilers actually, as I told you, some compilers use TAC, this 3 address code, as their intermediate representation. Okay, and some compilers use SSA. Okay, some compilers are there and they use SSA. In SSA also you have just like in TAC you have different definitions could be there, different some variations could be there. Similarly in SSA also you can have some variations, but the basic concept will remain the same. Just like in TAC you have the basic concept, like you must have at most 3 addresses. Similarly in SSA the basic concept is that you must assign to each variable you must have exactly one definition. So this is the basic concept of SSA. So it will remain the same in all the variations. Whatever variation you study for SSA, the basic concept will remain the same. And what is the basic concept of SSA? That each variable has exactly one definition. Okay, this is the basic concept of SSA. Now so okay, so you can see this this example. Okay, let's see this example. In this example you have, let's assume this type of program you have I equal to 0 and some statements are there, and let's assume that here you have if I less than 0. Now if I give you this type of program, okay, and now if I let's assume this type of 3 address code, if I give you, let's assume this is 3 address code. If I give you this 3 address code, then if I ask you, is this I same as this I? Basically, can I do this optimization? I want to do the optimization. Okay, the compiler want to do the optimization, that because he knows that I has the value 0. So why do this calculation? So just let's replace this I with 0. Let's assume my compiler want to do this optimization. Can this optimization be done? This is the question. So you have this program, and on this program can you do this optimization? Of course there is I here. So can compiler do this optimization? This is the question. Actually compiler cannot do this optimization. Why? Because this I is there and this I is there. In between it might have happened that I might have been defined again. I might to this I we might have assigned some other value in the between, you can see. Or it could have happened, for example, maybe after this statement some go to statement is there. Let's assume after this statement I is being assigned 20, let's assume. So basically after this statement I is being assigned 20, and now you have a go to statement, and this go to statement is taking you here. So you can see basically now when we go to this I, let's assume when we go to this statement, at this point of time we do not know whether this I is coming from here, basically whether this I should be given this value, or whether this I should be given this value, or whether this I should be given this value. We don't know these type of things. So that's why this optimization that we wanted to do, we cannot do this optimization. Okay, this is the problem you can see. So we wanted to do some optimization, but we can't do that optimization this easily. Now if I tell you that this is a static single assignment, okay, now I am telling you that this is a static single assignment, and now you have this statement. Okay, this is your program. So and I am telling you that this representation is SSA, static single assignment. Now can you do the optimization? Now you can say that yes, I can do the optimization. Why? Because you see in SSA this same variable will never be defined more than one time. This same variable I will never be assigned more than one time. Okay, so for example in between this I will never be assigned another value. Similarly after also this I will never be assigned another value. So that's why when you know that this is SSA, when you know that this program is SSA, okay, this program is in SSA representation, when you know this thing, then you can do this optimization. What you can do, you can basically remove this value, and basically you can do some optimization, because you already know that 0 is not less than 0. So you can directly take to the false branch. So this type of optimization you can do on SSA. As I told you, this is why we study SSA. This is why this SSA is so much important. Okay, because many optimizations are very easy on SSA, and this is just a motivation. This example I have given just to motivate you, like why we study SSA. This is the reason. This is one of the reasons. Of course we have many other reasons. When we will study compiler optimization, at that time we will see that this SSA is so much useful. Now I will share these slides. Okay, you can go through these slides also. Just don't read right now. So what is this SSA? In SSA basically each variable is defined only once in the program text. On the program text, remember this is the main important point. You have a text, you have a you can say you have a text, program text. In this program text your variable must be defined only once. Okay, this is the point. We will see some example, don't worry. So now again, how to convert? If you have a given program, let's assume you have a given 3 address code. That 3 address code, how can you convert into SSA? Okay, let's so how to do this conversion? Let's assume. So you can do this very easily. To do this conversion, what we do, we can use an algorithm, and that algorithm, what it will do, to each variable it will give some generation. Like when you are defining the variable for the first time, you can give it x0, zeroth generation. Okay, so what you can do, basically this is the first time you are defining it, so you can give it x0. Now whenever you will use it, then you can use it, no problem, you can use it. Okay, you can use it any number of times, but next time when you assign it, next time when you define it, then you can increment the generation. So basically you can increment x1 every time. Basically, of course, here actually you need to remember what is the generation of x. So let's assume the generation of x is 0, and let's assume some variable y is there and the generation of y is 0. So your algorithm has to remember these things, that what is the generation currently going on. So now at any point of time, if you again at any point of time if you again define this x, then you already know that now the generation has changed. So x has the generation 1 and y has the same generation 0, and now you can increment the generation. When you increment this, then you can again also modify the generation of the x. Anyway, this is just an algorithm. Of course, this is not that much important, because we can very intuitively convert the given 3 address code into SSA. You can see, for example, if you have this x equal to x into x, y equal to y into y, then you can very easily convert it into, first of all, this is the 3 address code for this program. This is the 3 address code. Now let's convert this 3 address code into SSA. So you have this. So this is your focus on this 3 address code. this is your 3 address code. In this 3 address code, actually this is the fetch definition. Okay, because when you supply this is a function, and to this function when you supply the value of x, at that point of time already x has some value, so x is already defined. So this is, you can see, so you can replace like this, x0 y0. So this is x0, this is x0. Now what you can do, you can write it x1. Now this is y0 y0, you can write it y1. Now what we are using x1 y1, this is t0. So this is how you can convert a given 3 address code into SSA. Okay, like this is the algorithm. Actually they have just given the algorithm, so they have just given the step-by-step implementation of the algorithm, you can say working of the algorithm. Okay, but we can very intuitively, without applying this algorithm, we can do this conversion. Like you have been doing, if you have already tried the SSA questions, at that point of time you did not worry about the algorithm. Okay, you just directly did it, so you can do it directly. Of course this algorithm will be useful when you have some complex questions. We will see some complex questions there, you need some algorithm. Okay, so now so this we have taken, I have taken from Ullman book. SSA actually has two properties. Okay, whatever variation of SSA you are using, two properties are there. The first property, that every variable will be defined exactly once. This is the first property. Okay, so the first property is basically that okay, every variable has distinct name. Okay, either you can say, because as I told you, like you wait a second, yeah, what we are saying all assignment in SSA are two variables with distinct names. So it basically means that you will assign each variable exactly once. That is the point. Okay, and the second point, so if you have this 3 address code, how can you convert it into SSA? Very easily. This is your A0 plus B0. Okay, and one more thing, let me tell you one more thing. This is your 3 address code. We take this assumption that before this 3 address code already A0, B0, all these things are defined, as I told you, because in SSA each variable is defined exactly once. So of course this is just a portion of the code. They have just given the segment, they have just given one segment. Before this A is already defined, B is already defined, and all these kind of things. Okay, so now what you do, so like this, when you reuse this P, then you can give it P2. When you reuse this P, then you can give it P3. Okay, so this is how you can convert 3 address code into SSA. Let's take some more complicated examples. Before that, let's see some theoretical points. Wait a second. Yeah, so these theoretical points are also important actually. Okay, because they just directly come from the definition of SSA. Okay, so first of all, this is a new intermediate representation. As I told you, don't think of it as a 3 address code. Don't think of it as a you know, some fancy 3 address code. Okay, don't think like that. This is a new intermediate representations. Okay, some compilers use this, some compilers use the 3 address code. Now it actually the concept that this SSA uses is def use information. Okay, this we will see in the compiler optimization also, but let me tell you what is the def use. Def use, basically def means definition, use means use. Okay, so in this basically whenever you have some 3 address code, in that 3 address code, of course you can define any number of times. So when we do some compiler optimization, at that point of time we use some def use chains. Okay, let me tell you some example. For example, x0 equal to x0 equal to x1. Now let's assume you do so you are defining it again. Let's assume, so some randomly I am writing. You can see, so if you have this type of program, then to optimize this program, okay, we actually some techniques are there, and those techniques, what they do, they make use of def use chains. So they will make some definition. For example, this is the definition. You can see this is the definition of x0. Okay, as I told you, assignment means definition. So this is the definition of x0, and this is the use. So they will make like this. They will make some chains like this, that okay, this is the definition, this is the use. Okay, like this is the definition, this is the use. So these type of course, okay, they will directly do the they will make all the change, and then they will do the optimization. Okay, now in SSA it becomes very easy, because in SSA you do not define same thing two times. Like here, actually what we are doing here, we are using this also, here we are making this also, here we are making this also. Actually we should make only this. Okay, but when you are doing the compiler optimization, then because of this you can see, because of these multiple definitions, you can see some optimizations actually become very hard. Okay, so that's the idea, you can say that's the benefit of SSA. In the SSA, each variable has exactly one definition. Remember this thing, every variable has exactly one. When we say exactly one definition, it means not less than one, not more than one. So like, don't do this mistake. For example, in GATE exam, when you see this type of statement, let's assume in the GATE exam they are giving this program and they are directly starting from x equal to y plus z, then remember that before this program they have defined it. Okay, this is just a segment of the thread. This is just a one block. This is one block they have given in the GATE exam. They have given one block. Okay, but before this block, this y is already defined. So this is the idea. Every variable has exactly one definition in the program text. Okay, I am focusing on this particular thing again and again, and we will take one example in the further slides. There is one example that will tell you why I am focusing here. Actually, this is the idea. See, when you have exactly one definition in the program text, then does it mean that you cannot have any loop? Like, see, take this example. Yeah, you have x equal to sorry, let's assume you have this x equal to t0 plus 1, something like this, and let's assume there is a while loop. Okay, there is a while loop, and of course this I'm just writing while, but of course this will be in the form of goto. Okay, but I'm just directly writing while to illustrate my point. Okay, so what I'm saying, this, you have this statement. So this is one definition. Of course, in SSA, each variable can have exactly one definition. Now let's assume that this while loop is going on 5 times. Okay, so in the body of while loop, you have this statement. Okay, this, wait a second. So you see, so this is the statement that you have in the body of while loop, and in this while loop, let's assume this while loop is going on 5 times. So you can see, of course, when this while loop is going on 5 times, then you can ask me, then how is it SSA? Because when this while loop will run for the first time, then this definition, this assignment means definition, then this assignment will be occurring. Then when this while loop will again run for the second time, then again this assignment will happen. You can see, for this variable, the assignment will happen again. For this variable x, the assignment will happen again. So if this while loop is going on 5 times, then for the same variable 5 times assignment will happen. So that's why you can see, that's why you might say that how is it SSA? Because this variable x, this is being defined 5 times, because this while loop is going on 5 times. So that is a legitimate doubt, but that is the point. That is why we are calling it SSA, means static single assignment, because this static single assignment, we only make it on the text. This is your program text. In the program text, you should not have multiple definitions. When you run this program, then you can have any number of definitions. Like in this, for this loop, this loop is running 5 times, so you will have 5 definitions, 5 assignment. Definition means assignment. So when this while loop runs 5 times, then there will be 5 assignments to the variable x. But that doesn't bother, that doesn't matter to us. That's why this is called static single assignment. Static means on the program text, when you read the program text, okay, when you do not run it, okay, don't run it, just look at the program text. In that program text, you should not have multiple assignment to the variable x. This is the idea. That's why it is called static. This is the word static. So this static word comes from there. So every variable has exactly one definition. This does not mean that you cannot have loops. You can have loops. Okay, you can definitely have loops. Okay, that's why this is called static single assignment, not dynamic single assignment. Okay, so okay, one more thing, just when you go to ISC in the first semester you will have two courses. One is PAV, programming analysis and verification. In this they do the static analysis. This complete course is based on the static analysis, and we have another course in the so in the first semester you have these two courses. Another is dynamic analysis. So these are two different courses. Okay, in this static analysis they just have the text, the program text. On this program text they do some analysis, do some optimization, do some type of things. Okay, they do not run it, they don't bother about the running of the program. Okay, they do not execute it, they do not run it, they don't care about the running of the program. They just do the static analysis. In this dynamic analysis they run the program. So when they run the program, at that time, at that point of time they do the analysis. So this is the meaning of static analysis and dynamic analysis. Static means program text, dynamic means basically you are running the program. Okay, so that's why this statement is I just wanted to clear this statement. What is the meaning of this statement? This is a static single assignment form, not a dynamic single assignment form. Okay, and of course why do we use this SSA? Because many compiler optimizations they perform better on SSA, as I given you one example. Okay, so some compiler optimization actually work very efficiently on the SSA forms. Okay, these are some examples. These we will see, because in the syllabus we have these type of things like constant propagation, live analysis. These kind of things we have in the syllabus. This year they have been added. So these things we will see. Okay, so you will see that these things actually work better on the SSA forms. So this is the use of SSA. Now so far we have only seen the when you have expressions. So far the SSA form we have seen for the expressions. Okay, now if you have loops, okay, if you have loops, then how can you convert it? Okay, let's take example. Let's assume this. In this you can see this is one basic block. Okay, you might already know what is a basic block. Basic block is nothing but a block from which you have one entry point, one exit point. This is the basic block. Okay, so for example this is your basic block. Okay, so this is the entry point and this is the exit point. Similarly, this is the basic block, this is the entry point, this is the exit point. Anyway, so this is your basic block. Here you have definition of A, definition of B. Now how to convert this into SSA? Let's assume I give you this. Then how can you convert it? So this is not in SSA right now. Why? Because this A has this definition here, this A has another definition here. So right now this is not in SSA form. How can we convert this into SSA form? So let's try to convert it. So this is A, this is B. If you directly do this, let's assume you directly do this, B here, B1 here, A1 here. Let's assume this is AB and this is B1, A1. Then what to assign this B? Let's assume you keep, okay, wait, let me assign it A0, B0. Now if you say that, okay, this is B0, okay, no problem, this is A0, is it okay? Just ask yourself, is it okay? We have now have we gotten the SSA form? Anyone want to tell me? Just by doing this, have we gotten the SSA form? Anyone? We have, yeah, we have only these variables. We only focus on these statements, only focus on these. Let's assume we have only 5 statements. These are the 5 statements we have. Have we gotten the SSA form? Let's see. Actually we have not gotten the SSA form. The reason is this: you have assigned the this n equal to B0 you have done. So this you have done. Basically you are saying that this n will get the value of B0 and B0 is this. But you see, you are coming from here to here, you are coming, okay, no problem. Then you are coming here. Now this n has B0. Very nice, very nice. Okay. Now you are coming here. Now you can go back here. You can go back here. Now when you go back here, then at that point of time, this B is actually B1. So what to put here? Basically, see, this was the original program. This is the original program. When you are coming for the first time, then this B is this B. N equal to B. This B is this B. But when you do like this, then this B is this B. So that is the issue here. You can see, are you getting some point? Like, this is the issue. So how to convert this program into SSA? Of course, these type of questions so far in the GATE exam they have not asked, but they can ask, because SSA in the syllabus is in the syllabus, 3 code is in the syllabus, and now this year they have added compiler optimization also in the syllabus. All these things have been added. So these are very valid things, because so far in the GATE exam they have only given the expressions, like these type of instructions, like t1 equal to t2 plus t2 plus t3, x equal to x plus y. These type of expressions they have given. For these expressions they were asking what is the SSA form, for the expressions only. But in the programming language we have expressions, loops, conditional statement, function calls, many things we have. Okay, even if we do not consider that, okay, even if these function calls and these kind of these kind of you can say hard things, even if we do not consider, at least we should know expressions, loops and conditional statement like if then. So these things at least we should know. Okay, so this example actually takes this example is a very nice example to see that you cannot just directly like, as I told you, I was telling you about one algorithm. At that point of time I told you that this algorithm might not seem important to you, because that algorithm will be very formal algorithm. You could directly convert the given TSE into SSA without any use of algorithm. You can directly convert. But you see, that algorithm was useful because these type of statements you cannot directly convert. Like, just like I told you that A0 B0, and if I write like this A1 B1, then it does not mean that I have gotten the SSA. Okay, so that is why algorithms, procedures, these kind of things are important. So let's see how to convert this given program into SSA. So we can convert it very easily like this. See, we know that when we go to this n, then this value b either can be this value b. Okay, first, okay, let me write it like this: A0 B0. First let me write completely. So A0 B0, and of course this is B1 A1, no problem in this. This is okay. A0 B0 B1 A1, this is okay. But what to put here? This is the question. What to put here? Whether to put B0 or whether to put B1, that is the question. So here, see, B0 can also be there, B1 can also be there. So what to do? When you convert this into SSA, then you remove this and you make a special function. There is a special function this SSA is providing. This special function is called phi function, and this will take two arguments, B0 B1. These two arguments it will take. This is the special function that we use, phi B0 B1. Why? Because at this point of time, this is, remember, this is the use, and these are the definitions. This is the definition, this is the definition, and these two definitions are reaching this at this place. So that's why we put phi B0 B1. It means that this definition is also reaching at this point of time, at this place. This definition is also reaching at this place. So that's why this phi function we use. Now this phi function, what it will do? This phi function will return the argument which is reaching. For example, for the first time when you are going, let's assume you are going for the first time. At this point of time, this phi function knows that you have taken this path. Because you have taken this path, so this phi function will return B0. Now in the second time, when you take this path, at this point of time, this phi will know that you have taken this path, so it will return B1. So this is how SSA works. Okay, so now similarly here, what to put here? A0 or A1. So similarly you can do again the same thing, phi A0 comma A1. So this is how you can do. So this is how you can convert this given statement into this given program into SSA. Okay, so actually this is the idea how you can convert a loop into SSA form. Oh, this is a very simple idea. You can see just a phi function, we just a new concept, phi function, this we need to apply. Okay, so like this. See, yeah, as I told you, here if we use this directly, then it might if this is a 3 address code, and if you convert this into SSA, then actually, okay, this is a small mistake I have done. you can just separately take one more variable a2, separately take one more variable b2. Okay, so this a2 will take phi a1 comma a3, this b2 will take phi b1 comma b3. Now this an can be assigned this b2. So like this is a small thing you just need to take care. Okay, so basically this phi function, we make a separate statement for phi function. Okay, so this is in the Ullmann. Actually in the Ullmann, on for when you study this SSA from the Ullmann book, then they have only one page. In that one page